Welcome everyone. Welcome to today's session. And from today, I'm going to begin the nuclear and particle physics revision. So this class will be from 3:30 to 5 p.m. And in this, we will start from the nuclear properties, goes towards nuclear models. And in nuclear models also, we will cover everything: shell model, how the shell model comes, binding energies, and all of that. And then we will go for radioactivity. Radioactivity will be covered from all the point of views. First of all, it will be covered from the basic radioactivity. And then also we will approach towards the selection rules, which are very important for CSIR net. And the basic radioactivity is important for other exams. And now afterwards, we will go towards the nuclear reactions, which are the hot topic from last 3 years in CSIR net and also in other examinations. And then we will go towards the advanced topics like scattering, deuteron problem, right? And the particle physics problems. So each and every PYQs which have been asked in CSIR net will be discussed in this, and from very basics to advanced. So if any class is only specific for CSIR net, I will let you know. If you are a BSc student, you don't have to attend that. But first few classes will be common for everyone because it is a fundamentals of nuclear. Okay, so we will try to do the syllabus in a fast track mode so that we can complete in 15 days. Okay, that is the idea. So today I'm going to discuss about the nuclear properties. Without going too much into the detail, we know that nucleus was discovered by Rutherford. So nucleus was an accidental discovery in which the Rutherford realized that entire mass is concentrated in a very small region, and 99% or 99.9% of the atom is empty. So he gave an idea of nucleus, which was later on more, you can say, supported by other scientists as well. And we got a nucleus in our hand. Then we realized that nucleus is basically contains positive charge because it has protons. And in the earlier stage, it was mentioned that it was assumed that nucleus contains electron as well, because in a beta decay, electron comes out of the nucleus. But that later on proved to be wrong. The nucleus does not contain electron. Okay? And there are multiple reasons for that. Uncertainty principle is violated. Spin or magnetic moment considerations are violated. And other reasons are there as well. Because in a beta decay, the electron comes out with a very small energy. But in reality, if electron was inside nucleus, it should have come out with huge amount of energy. But that is does not happen. ठीक है, that also we will understand कि if nucleus does not contain electron, then how come in a beta decay electrons comes out. ठीक है, that is also will be discussed. But then Chadwick came in 1932. In 1932, Chadwick came and he gave an idea of neutron, which is a basically a neutral particle, and it is responsible for the mass of the nucleus. So we were not able to understand why the mass of the nucleus is so high, because so is it because of all the protons? But no, he says roughly half or more than half of the mass is because of the neutrons. Okay, so neutrons were not discovered till a very 1932, which is a long time. uh, Between proton discovery and neutron discovery there is a huge amount of time, and especially between electron discovery and neutron is a lot of time. And the reason being, neutron was a chargeless particle. There was no charge, so it was not easy to detect this particle. Okay, and later on it was discovered by Chadwick. Now there are few questions about nucleus. We want to understand about nucleus, and in this attempt, we will make some attempts. Number one, what we want to know is what is the size of the nucleus? What is the shape of the nucleus? What is the constituent of nucleus? Okay? What makes nucleus? A simple model is like proton and neutron. But a complex model comes in a particle physics. It is made up of so many things. Okay? Then what is the energy of the nucleus? How much is the stability of the nucleus? And things like momentum of the nucleus, form factor of the nucleus. These kind of things we will answer in next few classes. We will understand each and every aspect we want to know from our competitive exams point of view about the nucleus. And in this context, the first thing that comes to mind is the nuclear radius. Now, nuclear radius you might think is very easy thing is to define, but actually it is not. Okay? Because nucleus is not like a tennis ball you have. Tennis ball is very clear. Tennis ball, if you hold in your hand, it has a very sharp boundaries. You can see that, okay, here the ball ends. But nucleus in reality is not like that. There is no sharp boundary where you can say, okay, here the nucleus is gone. Okay? No, nucleus is you can say imagine it. We can assume it to be sphere, but we will also talk about that in a collective model of nucleus. That nucleus is actually not completely sphere. We define quadruple movement to make sure that it is actually deviated from sphere, just like Earth, right? So that is a higher order perturbation we will add to it. Okay. So how do we define nuclear radius? Because it do not have any sharp boundary. And if something do not have any sharp boundary, so how do you define the radius? Because if you have a sphere, it is very simple. If you have a tennis ball, you know the ball will end here. So the distance from center to the surface is a radius. But if something does not have a sharp boundary, then what is the definition of a radius? For example, clouds. If you look at the clouds, the central part is white, but the outer part is foggy. It is transparent kind of thing. So then, what exactly is your radius of the cloud? That is the problem. Okay? And how do you know? How do you experimentally know this is a radius? So experimentally, between 1800 to 1900, or even till now, the experiments were very much pro-dominant, which are scattering experiments. Many Nobel Prizes came out of these scattering experiments. Rutherford scattering experiment. Don't think that the scientists were so genius they conducted an experiment after the planning. No, no one in this physics field performs an experiment by planning. Okay, they just follow a rat race. Okay, everyone is doing, for example, these days everyone is doing quantum experiment, so everyone is going for that. In that era, everyone was doing scattering experiments. Everyone. Okay, so you get a funding for scattering experiments. But is scattering experiments, take some particles, move them at very fast speed with whatever methods you are having, and then collide it on the materials, different materials. So if you open up the papers, there are millions of papers you will find having a different particles bombarded on the different materials. And out of these millions of papers, few papers changed the field of physics. For example, Rutherford paper. For example, many other papers as well you can imagine. One of those experiments is this. You are bombarding the particles on a nucleus, basically some material, and then they are scattering. The particles are scattering, and then you do the back calculation, and then you predict about the size of the or the shape of the nucleus. So this is what happens. You throw the particles on your material. So this material is nucleus. So basically material contains nucleus, and this particles comes and scatters from the nucleus, and then you on the screen you observe these scattered particles. Then you do the back calculation. Okay, if this kind of scattering is happening, it means the shape of the nucleus and the size of the nucleus should be like this. Okay, and then that size is being given in the paper. Okay, this is my picture of the nucleus, which I back calculated from the scattering experiment. Okay, and this was the image which was published by many scientists combined together. Everyone agrees to this image. Okay, what is this image and what is this image tells you? So this graph basically is a graph between charge distribution, how the charge is distributed in the nucleus as a function of r. So r is a distance from the center, and rho is a charge density, means charge per unit volume. Okay, so at the center, what is the charge density? Some distance far from the center, what is the charge density? So how the basically protons and neutrons are placed inside the nucleus? That is this graph tells you. This graph basically tells you how the protons and neutrons are placed inside the nucleus. Basically nuclear structure. And the same thing happened in the atomic physics also. Atomic structure also came in a very similar. Okay, that was the first attempt. After the atomic physics, we went into nuclear physics. Okay, so if you keep on increasing the energy, if your particles are slow, you will get an idea of the surface physics. You increase the energy, you get an idea of the atomic physics. You increase the even more energy, you get an idea of the particle physics. Oh, sorry, nuclear physics. You increase even more, you get an idea of the particle physics like Higgs bosons, and those kind of ideas. Okay, so we are now in an energy level in which we are understanding the knowledge of nucleus. Okay, so what does this graph tells you, and how do we define the radius from this graph? Very important. And in TIFR, directly this question has been asked. This graph is directly asked in TIFR, direct. So yeah, so what is this graph about? So this graph states few things. Number one, the central density is constant and it is same for all the nucleus. So you see, in the center, the density is almost constant. It is not changing with the distance. So if I start drawing out, so this is a central part of the nucleus and this is almost constant and it is not changing with distance. Everywhere it is same. So you can imagine it like a cloud. In the cloud, you know, the central part is very, very bright white colored. So that is the central part of the nucleus. And if you find this density, it will be rho naught. And this rho naught is same for all the nucleus. Uranium also has the same central density. Hydrogen also has the same central density. Lithium also has the same central density. So two things. One, it does not change with distance. Second, it also does not change with nucleus. So every nucleus has almost the same central nuclear density. Okay, so that is the first state. Okay, and how do we get this graph? Through the scattering experiment. Okay, back calculation of the scattering experiment. Second, nuclear density decreases after some distance from the center. So as you go away from some distance from the center, the nuclear density will start to decrease and ultimately it will become zero. Okay, so in the center you have a very, very dense material and then the density keeps on decreasing. You see the dots are getting far and far away from it. Okay, far and far away from it. Right now we are not answering the question that why the nucleus is like that. Right now we are answering the question that what do we understand from the experiment. The answer to this, why the nuclear radius is like that comes from the quantum mechanical calculation. So first you assume it to be an infinite well, then you add on more and more complications, and then you get to this picture. Okay, then you know nuclear forces, Yukawa potential. So you take all of these considerations and then you try to replicate this graph through theory. Okay? That is another branch, right? Not branch, but this is another field of study. Okay? But one thing we understand is that after a certain distance, if you go away from the nucleus, the density will keep on decreasing. So imagine it like a student sitting in a row, in a circle. So in the middle part, students are almost sitting like very close to each other. As you keep on going away, in one circle, only 10 students are sitting. If you go away, in one circle, only 5 students are sitting. If you even go away, in one circle, only 2 students are sitting. So as you are keep on going away and away, in one circle, the number of students keep on decreasing. It means the density of the people or the proton and neutron density keeps on decreasing. Okay? So ultimately, when there is a circle when no one is sitting, we say, okay, now the nucleus is end. Okay? So it is like the kind of situation, let's say in your school, H.C. Verma sir appears. Right? So H.C. Verma sir comes. Now we all will get excited. In your college, H.C. Verma sir is coming. So what will happen? The people will surround. So people will surround H.C. Verma sir. So where the H.C. Verma sir is there are many students will be there. So almost density will be same. But as you keep on going away from H.C. Verma sir, the number of students will be keep on decreasing. But no one can exactly say where will this end? Where will this end? No fixed idea. There is no sharp boundary. Okay, after this boundary, no student is there. That is not fixed, defined. Right? Yes, that we can agree. As we keep on going away from H.C. Verma sir, the number of students surrounding will keep on decreasing and decreasing. Right? 2 kilometers away, there will be no one waiting for H.C. Verma sir. Right? So that is a kind of a nuclear shape we have. Perfect. So in such kind of shape, how do we define a radius? That is a big question. Okay? So radius, which is capital R, is a distance. This is a scientifically accepted definition. Radius R is a distance at which the density becomes 1/2 of the central density. So the distance, so this distance where the density has actually become 1/2 of the central density. So you see at this point, the density has become half of the central density. Okay. At this distance is defined as a radius. So we will say, okay, our nucleus is only till this point. So this is your radius. That's all. So this is a accepted definition. It's not like that beyond this no one is there. Yes, still beyond this also few people are there. Less than this are also people there. So this R does not mean that there is nothing beyond that. Just like a classical physics, what do we say? If the radius of the tennis ball is this, then beyond this there is no one. Ball is not there beyond this. But in this case, it is not true. We define radius in this way, but even beyond the radius, we have the nucleus. But the way of defining the radius is key. The radius is a distance at which the density becomes 1/2 of the central density. And now the formula of this radius is very, the formula of this radius is r equals to r naught a की power 1/3. ठीक है. Now r naught is some constant. Its rough value is 1.2 femtometer or fermimeter. Femtometer or fermimeter is almost 10 की power minus 15 meter. And the value of this r naught depends upon the experiment that you are using. So in different experiments, the value of this R naught will change. It will not change too much. It will change from 1.2 fermimeter to roughly 1.5 fermi. But it will change. Okay? Because the R naught is an empirical constant and its value is decided by the experiment. Perfect. But what is A? A is a mass number. So you know, whenever you define a nucleus, so you first write the symbol of the nucleus: chlorine, Cl, hydrogen, H, carbon, C. In general, we say X, right? Then you define atomic number, which is Z. Now Z is the number of protons. And then you defined A. A is the mass number, which is number of protons plus number of neutrons, right? So total mass. It's not total mass, it's total mass number. Okay? So carbon has 12, oxygen has 16, hydrogen has 1, helium has 4, right? So that is a mass. So you can clearly see that the radius will increase with the mass, but not that much, because there is a power 1/3. Okay? So this formula is the most important formula for our exam point of view, and this graph is the most important graph also from our exam point of view. So now we understood that how the radius came, how we define the radius for a nucleus, and how the density of the nucleus varies with the distance. Constant, then decreases, and then 0. Okay? The density is half, whatever point that is the radius. Done. That is what you need to know in this topic. Okay? Any doubt in this till now? Now, next idea is key. How do we define the volume and density? Okay? So volume is very simple. So assume, first of all, the first assumption is assume the nucleus to be sphere. Assume. I'm not saying it is sphere. Later on, even I will prove you that it is not sphere. It is little deviated from sphere. But a good assumption is it is sphere. So if we assume nucleus to be sphere, then the volume is given by 4/3 pi r cube. And we have successfully defined the radius, which is r equals to r naught a की power 1/3. Now, if I cube this, I will get r naught का cube, and this will become a. Okay? So volume is directly proportional to a. So that is the first thing that I learned. Second, what is the density? Density is mass per unit volume. So mass is the total mass of the nucleus divided by volume, which is 4/3 pi r naught cube a. How do you define the total mass of the nucleus? So you say, so let's say I have this nucleus. Okay? A is known as the protons plus neutrons. In nuclear physics, usually we do not like to name them separately. We just call them nucleons. So nucleon is a common name for both of them. Okay? So whenever you say nucleon, you might be talking about neutron, you might be talking about proton. You can call both of them nucleons. Okay? So capital A is the mass of the, capital A is the number of the nucleons. So what is a mass? It is how many nucleons you have multiplied by the mass of each nucleon. Okay. For example, in carbon, you have 12. So what is the mass of carbon? 12. And then you write AMU, right? You remember? You don't just say it's 12. You say it is AMU. And then you know what is AMU. AMU is 1.67 into 10 to the power minus 27. Okay. So basically what you are saying here is that you have 12 nucleons and the mass of each nucleon is 1 AMU. So the total mass is 12 AMU. The same thing is here. The total mass of nucleus is number of nucleons multiplied by the mass of each nucleon, which is 1 AMU. Okay? Mass of one nucleon is 1 AMU. Atomic mass unit. Perfect. So then it is simple. A and A can be cancelled each other out, and then you get 3m by 4 pi r naught cube. And the important fact is that this is constant. 3 is constant, AMU is constant, 4 pi is constant, r naught is also constant. So this is a constant number. That is why you see the central density was constant. It was not changing with distance. It was not changing with nucleus. And what we are calculating is the central density. Okay? So whenever you use this formula, R equals to R naught A1 by 3, it means you're talking about the central density. And it is constant. And if you calculate this value, you will get roughly 10 to the power 17 kilogram per meter cube, which is highly dense. 10 to the power 17 kilogram per meter cube. It is more dense than anything you have ever seen. Okay? But still, since most of the space in an atom is empty, so high density of nucleus does not make us very highly dense. Okay? Nucleus is dense, but we are not dense because nucleus is a very small part of our atom. Okay? If our entire atom was this much dense, then our density was even more than I think most of the stars. Okay? Yeah. So what are we going to remember from this? The volume is directly proportional to atomic number, sorry, mass number, and our density is constant, central density, and its value is roughly 10 to the power 17. So remember this number, 10 to the power 17, very important number. Okay. So yes, if there is no doubt, I will go for the problems. Yes. Anyone likes to ask anything here? कुछ भी थोड़ा सा भी समझ नहीं आया है तो प्लीज डोंट हेजिटेट. ठीक है. Maybe sir, electron is nucleon? No, electron is not nucleon. Electron is separate thing. So electron is a separate thing. Nucleon is a name given to either proton or neutron. That's all. Okay. So proton or not neutron, both are, yes, it is in a geophysics syllabus. Direct questions will come. Direct. Whatever we are covering today will be directly asked in UPSC geophysics. Right? Okay. This is the reason for a small size. What is the reason for a small size? Sir, we talked about the mass density of the nucleus. Do we need to? So for now, we are assuming mass density and charge density to be same because we are focusing on the proton. Okay? We are focusing on the protons and not same. There are two kinds of experiments you can do. One is the electrostatic scattering, in which you get charge density, and another is the gravitational scattering, in which you can get is a mass. Okay? It is always easy to do electrostatic scattering, and right now if we can find one of them, we will assume that second one is also following the same trend. So that is an assumption underlying this. Okay? Perfect. Anything else? So for now you can assume mass density and charge density are doing the same. They are following the same trend. Okay? Okay. Sir, where we are assuming mass of protons and neutrons same? No, we are not assuming to be same. We are calling them by the same name. Yes, in general, in theory, we say, okay, mass of the neutron and mass of the proton, both are 1 em. But there are small difference. Mass of the neutron is slightly more heavier than mass of the proton. Okay? I don't know what is, no, neutron star mean, yeah, neutron star is basically when atoms squish together and all you are left with is the nucleus. Okay? So yes, that is a reason. Anyway, when you keep on squishing the things, the density will increase. It's not in only the neutron star, but in all kind of stars, you see the material is getting squished and the density keeps on increasing. Okay. Okay, now let's come to the problems. The first problem is from the JAM. Very simple problem, starting with the very simple one. So there are two spherical nuclei ठीक है. They have the mass number 216 and 64. So A1 is 216, A2 is 64. Then they are asking what is the ratio of the radius. So you know radius is directly proportional to A1 by 3. So A1 by A2, A1 by R1 by R2 will be A1 by A2 की power 1 by 3. ठीक है. So then A1 is 216 and then A2 is 64, इसकी power 1 by 3. Now 216 is a 6 का cube and 64 is a 4 ka cube. So cube and 1 by 3 will cancel, so you will left with 6 by 4. 6 by 4 is nothing but 1.5. That is why the answer to this problem is 1.5. Okay, is this question clear, everyone? The similar question has been asked in CSIR net. I did not include that because it was a very straight question. One question also asked in JEST. So this formula is directly asked, and if this is asked, it is very lucky of you that they are asking you the simple question. Okay. Okay. No, electron can never be said as nucleon. You can give me the screenshot of the book. No book says that electron is a nucleon. Okay. They might have a different context there. Okay. There was one model in which initially it was assumed that electron was inside nucleus, but later on that model was rejected. Clear. Now the next problem, this kind of problem is there in JAM, but also asked in CSIR. So CSIR net also asked this similar question. So I have only taken one of them. So what is the question? Question is the mean momentum of nucleon. When they are saying nucleon, so they might be talking about proton or neutron. So nothing. You don't now stop distinguish between them. ठीक है, दोनों के बीच में फर्क करना we will stop. So they are asking what is the momentum of the nucleon. So inside the nucleus, the nucleons are there, and nucleons, what is the momentum of the nucleons? ठीक है, how does this momentum depend upon atomic number or the mass number? ठीक है, mass number or atomic, how does they depend? How does momentum depends upon them? That is what they are asking, and they will never ask you the exact value. They will always ask you the dependence. Okay. So what can we do? So the best idea to connect the two is uncertainty principle. Not just in this case, but in many cases you can use this. So how can you use uncertainty principle? So uncertainty principle says that the uncertainty in position into uncertainty in momentum is greater than or equals to h cut by 2. Okay. What is uncertainty in distance? So let's say I ask you, okay, your nucleon is inside this sphere. Your nucleon is inside this sphere. So I did not told you ki where exactly. So it can be here, it can be here, it can be here, it can be here, anywhere it can be. So you have some uncertainty. You don't know exactly is where your nucleon is. You know that it is within this sphere, but you don't know where exactly it is. So there is an uncertainty in the position. So uncertainty in the position is equals to the radius. So delta x is equals to radius. So the value of position can be anywhere from r equals to 0 to r equals to capital, right? So the uncertainty in the radius or uncertainty in the position is actually capital R. Okay? Because it can be anywhere in the nucleus. That is why you say delta x is capital R. Okay? And you know capital R depends upon A1 by 3. Okay? So that is what you see. So it means that delta P is inversely proportional to A1 by 3. Okay? And if I take it in the numerator, so P is directly proportional to A minus 1. So the momentum is depending upon A ki power minus 1, which is your option number C. Okay? So first I said delta x into delta P is h cut by 2. Then I say, okay, delta P is inversely proportional to delta x, right? And delta x is directly proportional to radius. So which it means it is directly proportional to A1 by 3. It means delta P is inversely proportional to A1 by 3. It means it is directly proportional to A minus 1, which is your option number C. So that was your question. That is how you understand ki how momentum depends upon A, mass number. Okay? Any doubt in this problem, anyone? Is it clear to all of you? Then we go for the third question, and third question is very straightforward. And again, it is from a JAM and it is a theory based question. So this is the relation between the nuclear radius and the mass number is given by this. So they gave you the relation which we studied. Then they says that this relation implies, what is the implication of this formula? So implication of this formula is the central density of the nucleus is independent of A. Yes, that is true. So that is your answer, right? What was the implication? If the radius is this, then what is the implication? Then you saw that density is what? Mass by volume, and mass is small m into A, and this is 4 by 3 pi r naught cube into A. This density is not dependent upon A. Why? Because your radius is changing like this. Because your radius has this formula, that is why your A and A is getting cancelled with each other. You cannot change anything else in this formula because you cannot change mass. Mass will always be A into small m. All you can change is a radius. And since your radius has this formula, that is why your capital A and capital A cancels. And that is why your central density does not depend upon A. So the implication of this formula is your option number A. Okay? The volume energy per unit nucleon is constant. These all things are not. Okay? Nuclear force is charge dependent. These things are the random statements which are given. They have no relation with this formula. Okay. So option number A is correct. Yes. Any doubt in this one? So that is why the story of the formula is also important, because if you know the story of the formula, they can even ask the question from it. Okay. So you know that this formula we defined because central density was constant. Yes, clear. Okay, then we come for the question number 4. Again, this is not from JAM, sorry. This is from CSIR net. So this question is from CSIR net. Okay, yeah, good. Excellent question. And this question will even give you one more fact about the nucleus. And what is that? Let's understand. The root mean square energy of the nucleon in a nucleus in the ground state, how does it depends upon A? So basically they're asking root mean square energy, how does it depends upon A? So basically, kiski energy? Energy of the nucleon. So inside your nucleus, there are nucleons. Nucleons have momentum. How momentum are related to A, we found out. They also have energy. So now they're asking how the energy is dependent on A. That is what we will answer. So how does ERMS depends upon A? Okay. So yes, one thing that we know is that momentum depends upon A ki power -1. That is our starting point. We know that momentum is A ki power -1. Now we want to know what is the relation between energy and momentum. How does energy depends upon momentum? And the two formulas comes to my mind. One is a non-relativistic formula. When my energies are non-relativistic, means the energies are much greater than the rest mass energy. Okay, basically I don't have to take a relativity. Then in that case, energy is p square by 2m. And one formula is used when you have a relativistic conditions. In that, energy is given by p square c square plus m naught c is 4. So this is rest mass energy. And then this is p square c square. Okay. Now the question arises, is our nucleus relativistic or is our nucleus non-relativistic? So the energy of the nucleons comes under the relativistic approach or non-relativistic approach. So the answer is it always comes under the relativistic approach. Energies are very high. Energies of the nucleons inside the nucleus are very high. So what we have to do is we have to take a relativistic calculations always. Okay. In atomic physics, we usually ignore relativistic and we go for non-relativistic. Usually, we also consider relativistic at the later stage, but that consideration is very small. But in nucleus, you cannot do that. If you are finding the energy of the nucleus, the calculations which will be obeyed will be relativistic. So if it is relativistic, then it is very clear that energy is directly proportional to P, because if you take the under root of this, you will get P, right? So if I talk about the order, energy is directly proportional to P, and you know P is A1 by 3, so E is also A minus 1 by 3. So from here I get an idea that energy is also depending on A ki power -1 by 3, which is your correct answer, which is your option number C. But now you see, look at the point. If you take this formula, because you might remember this formula. Then you see energy is directly proportional to p square. In that case, energy will be a ki power minus 2 by 3, and that is also an option. And in this way, CSNet wants you to give this wrong answer. That is why they put you in that option. But the correct answer to this question is C, because you cannot take the non-relativistic formula. You have to take a relativistic formula. In that context, energy is directly proportional to P, or you can say energy is directly proportional to a ki power minus 1 by 3. So option number C makes complete sense. Yes. Any doubt in this one? If the dependency of velocity with A, then how to approach? Then dependency of velocity. So once you know the momentum, then velocity also do the same thing, right? Because momentum is nothing but mass into velocity, right? In case of electron, then it will not be that simple, because then you have to use this formula. Momentum will be m naught v into 1 minus v square by c square. And then you know P is a ki power minus 1 by 3. And then you solve this out and then find how v depends upon A. Okay? No, it is not going to 0. I'm not making it 0. Okay? I'm not making it 0. I'm just trying to understand the dependence. Okay? Dependence. Okay? How does E depends upon P? Okay? I'm not making this. Never. That is not 0. In case of electron, we consider non-relativistic. Yes, as long as you are in atomic physics, you are studying the Bohr's model, you take it to be non-relativistic most of the time. Okay? But there is, hyperfine structure. In hyperfine structure, you take the relativity. Okay? So I'm not saying always, but yes, 99% of the times you take it to be non-relativistic. But when you are studying nuclear physics, it is not possible to take it non-relativistic. Clear? So that this difference should be known. Why I did not use this formula and why I use this formula. Okay. Most of the books and most of the solutions directly use this formula without explaining why we use that. Clear? Okay. Yeah. So this was the topic on radius and the, you can say, is the volume and the density. Okay. Now I will go for another topic, which is mass defect and binding energy. Very important topic. So we will take just 31 minute of break and then we will do for this topic. Okay. Yeah. Let's take a stop for 1 minute and then start. So what is mass defect? So mass defect is a very simple concept. And you don't only see this in nucleus, but we see this in almost every part of our life. Okay. So basically, we take an ingredients and we make something. So let's say we take an ingredients of 10 kg. 10 kg of ingredients we take, different ingredients, and we combine them together and we build something. The mass of the final product will not be 10 kg. Some mass will be lost in between. That is mass defect. Every branch of the science has this mass defect for a different reason. For example, in cooking, the mass is gone in evaporation, right? The water loss, and so on. In mechanical engineering, mass is gone because of the friction, right? In nuclear physics, in chemistry, the mass is gone because of the chemical reactions and the energy released in the chemical reactions. But in the nuclear physics, this mass defect is purely a physical phenomenon. So it follows the Einstein's principle, in which Einstein says that mass of a body can convert itself into energy. This is a half truth of the Einstein's principle, because this is happening every day. Mass converting into energy is not a Einstein's idea, right? If you burn the candle's mass will convert into energy. So mass is converting into energy. What's Einstein here? So Einstein says the mass is converting into energy through a physical process, not through any chemical, not through any biological, but through a physical process. So someone was running, and while running, his mass converted into energy. No chemical reaction. That is something surprising. So that was an Einstein's idea, that mass converts into energy through a physical process. And that is what happens exactly inside a nucleus. Okay? So the mass defect is a mass of the nucleons. Nucleons are the ingredients. Okay? So ingredients. So let's say you take 10 nucleons. So the mass is 10 AMU. And then there's 10 10 people combine together to make a nucleus. Okay? But the nucleus will not have the mass 10 AMU, it will have the mass 9.8 AMU. So 0.2 mass is gone. 0.2 mass is gone. Okay? So mass defect is what? Mass of the nucleons minus mass of the nucleus. Okay? Nucleons are the ingredients which makes up the nucleus, and nucleus itself is a final product. Right? So that is the idea. For example, in case of a helium, so if I take a helium, the mass is atomic number, mass number is 4. So the mass of the nucleus is nucleons is 4 AMU. But when the final helium will be produced, it will only have the mass of 3.9 AMU. So it means 0.1 AMU mass has been lost in this process. Okay? So mass defect happens during the production of nucleus. So that is the idea. So that is how do you make the formula for that? For example, if I'm talking about this nucleus, which is X is any symbol, Z is the atomic number, A is the mass number. And let's say the mass of this nucleus is this. It is given. What it is, I don't know exactly, but it is given that mass of this nucleus is M. Okay? So how do you decide this? How do you decide this? So first you write the mass of the nucleons. So how many nucleons you have? So you have Z number of protons and A minus Z number of neutrons. So this is your protons and this is your neutrons. So you will say Z into mass of protons plus number of neutrons into mass of neutrons. So this is your total mass of ingredients. This is the mass of the ingredients. You have Z protons and A minus Z neutrons. So what is the mass of the ingredients you have? You have Z into MP plus A minus Z into Mn. That is the mass of the ingredients minus mass of the final product that you have. So final product is nucleus. So what is the mass of the nucleus? Okay? Both of them will not be same, and if you subtract them, you will get some small number, which is your mass defect. Okay? So where is this missing mass going? You have the mass missing. You took the 10 kg of ingredients, you combine together, final product has a 9 kg. So where is 1 kg gone? Where is that 1 kg? So that missing mass is converted into energy using the physical process. So that mass is converted into energy, and that energy is used to make the nucleus. So why we need energy to make the nucleus? Anyone? Why do we need energy to make a nucleus? Anyone?
To do work
What is
against electrostatic force.
Yes, to do the work against electrostatic force. Because you see, if you want to make a nucleus, what do you exactly want? You want keep protons and protons comes together and hug each other. Hug each other, right? So initially they will not hug, because when they are far away from each other, there is a repulsion between them. But when you bring them so close to each other, the nuclear force dominates and then they hug each other. So that is like a Ukraine and Russia is fighting with each other, right? They will hug each other, but someone else needs them to bring them close first. So until unless we don't bring them close, they will not hug, right? So we need to do some work to bring these protons together, and in order to do that work, we need energy. And from where we will bring that energy? So think about the universe. There was no one to create the universe. Universe has to create itself, right? So then universe thought of a very clever idea. So universe said, okay, I have 10 kilogram of ingredients. Okay, so let's use 1 kilogram of ingredient and convert that into energy, and then use that energy to make the final recipe, to make the final nucleus. That is why the final nucleus will not have 10 kilogram weight. Instead, it will have 9 kilogram, because universe used 1 kilogram to make this recipe, make this cooking done. So that is what exactly happens in a nucleus. So yes, that is an idea. So in order to make the nucleus, we need energy, and that energy comes from the mass. That is why the mass is lost in the process. And it is lost using a pure physical process, no chemistry, no bioism. Okay. Then here comes the definition of binding energy. So binding energy basically is defined as what is an energy required to form a nucleus or to break the nucleus. It will be exactly same. So whatever energy you need to form the nucleus will be same as the energy you need to break the nucleus. So you can define your binding energy in any terms. So we are defining it in this term. What is the energy required to form a nucleus? So binding energy will be very simple. Binding energy will be just mass defect into c square, right? Because how much mass is converted to form the nucleus? Mass defect into c square. 1 kg, na? 1 kg mass was used to convert into energy, and converting energy was used to form the nucleus, right? So how you convert mass into energy? You multiply by c square. You know this formula, E equals to mc square. So what is the mass here? Mass is a mass defect. Okay? So binding energy mathematically is defined as delta m into c square. Delta m is the mass defect, which is the difference in mass between प्रोडक्ट का मतलब इंग्रेडिएंट्स का मास माइनस फाइनल जो बना उसका मास. चलिए बात करते हैं नेक्स्ट. There is some facts you should know कि one atomic mass unit is 1.67 into 10 to the minus 27 kg, and if you convert this into energy you will get 1 amu into c square, which will be 931.5 mega electron volt. If someone does not know, electron volt is equals to 1.6 into 10 to the power minus 19 joule. So it is a units of energy. Okay? Especially when we are dealing in atomic and nuclear physics, the energies are defined in terms of electron volt. Clear? So yes, that is the idea. So, but the important fact here is that binding energy is not that important parameter. Binding energy per nucleon is a more important parameter. Okay? Why? For example, if you are cooking dal, so if you are cooking 1 kilogram of dal, you need binding energy of 10. If you are cooking 100 kilogram of dal, then you need 1000 energy. That is obviously makes sense. But what you want to know is ki what is easier to cook, dal or chai? Okay. Now, if someone asks you which is easier, cooking 1 kilogram of dal or cooking 100 liter of chai? So you obviously you will say 1 kilogram of dal is easier to cook. But this is not because dal is easier to cook. It is because the quantities are different. If we really want to compare them, then we should compare energy per unit nucleon. So if I say, okay, dal needs 100 energy per kilogram and chai needs only 1 energy or 10 energy per liter. Now what is easier to cook? Obviously chai is much easier to cook. You can cook a chai in minutes, but dals will take little bit. Okay? So what is important parameter here is binding energy per unit nucleon is more important than a pure number of binding energy. Okay? So binding energy per nucleon tells you about the stability of the nucleus. If the binding energy per nucleon is more, then your nucleus is more stable, because it means more energy has been spent to make this nucleus. That is why this nucleus will be more stable. It will not break. It will not have the radioactivity. Okay? So more the binding energy per nucleon, more is the stability of the nucleus. Okay? That is the most important. Now in this class, I will means complete how does binding energy per nucleon depends upon the nucleus. Basically, if I make the graph of binding energy per nucleon versus A, means I take different nucleus and I try to understand how the binding energy per nucleon is changing experimentally what we observed. And then in the next class, I will try to explain through the models why this graph comes. Okay? What is the explanation for this graph? So let's understand. So few things we have understood. There is a mass defect. Then mass defects convert into binding energy. And binding energy is not important. Binding energy per nucleon is important. And binding energy per nucleon is tells you the stability. If binding energy per nucleon is more, stability is more. Don't think why. I will explain that in next page. Okay. Right now, keep your minds calm and accept my idea. Okay, binding energy per nucleon is more. It means the stability is more. Why? I will explain in a bit. Okay. But first, let's understand. If I change the nucleus, how does my binding energy per nucleon changes? Okay, perfect. So binding energy per nucleon versus A follows this very interesting graph in which you have peaks and then you have this kind of tomb. So this is your graph. There are few parameters in this graph which are very interesting. Number one, and all of this you need to keep in mind, you need to remember the curve is constant in the middle. So in the middle region, you see the curve is constant, not exactly constant, but almost constant. You see, it's not changing that much, right? It's almost, you can find an average line. So whatever above average and below average are same. So almost a constant thing you have. I'm not saying it's exactly constant. Okay, it is not, obviously it's not exactly constant, but they are almost constant. So in the middle of the graph, the binding energy per nucleon is almost constant, and its average value is 8 mega electron volt per nucleon. This is an important number. 8 mega electron volt is an important number. So if someone asks you in the middle region what is an average value of binding energy per nucleon, it is 8 mega electron. Keep this in mind. Okay? Then another important fact is this peaks. You see, this peak, this peak, this peak. So you don't have to remember that where are these peaks coming, but these peaks comes at mass number 2, mass number 8, mass number 20, mass number 28, and so on. So you get a peaks. So these peaks are known as the magic numbers. What are the implications of these peaks? So if you talk about the peak, so it means this nucleus is more stable than its neighboring nucleus. This one is more stable than this one. Also, it is more stable than this one because its binding energy is more compared to left as well and compared to right as well. Whenever you have a peak basically defines the, okay, I am greater than my left person, I am also greater than my right person. So that is why I am at the peak, right? So these nucleuses are more stable than its neighboring nucleuses, right? And why? So some people connect this idea with the filling, half filled and full filled orbits. So you see in atomic physics, we know when the orbit gets fully filled, the stability increased. Similarly, some people, or in some models, we assume that even nucleus also has the orbitals. And when the nucleons are getting filled in those orbitals, whenever you have the half filled orbitals or full filled orbitals, our stability increases. So that idea is connected with the half filling and full filling of the orbitals. So these magic numbers are explained on the basis of that. Okay, we don't have to go in too much detail and exactly prove it, but we should know that from where its significance is coming. So magic number says that these nucleuses are more stable than its neighbor people. And why? Because at these nuclear levels, the half filling and full filling of orbitals is happening. So two facts are clear. Third fact, iron nucleus, not iron atom. Iron atom and iron nucleus are two different things. Iron atom is an atom, but if you remove all the electrons and only thing that is left is nucleus, that is what I'm talking about. So iron nucleus has the most binding energy per nucleus. That is why you see at the top iron is sitting. It is most stable and its value is 8.7 into 10 ki power 8.7 mega electron volt into by nucleon. Means its per nucleon energy is 8.7 mega electron. So iron will never go radioactive. Means iron will not be radioactive. It does not mean iron itself is stable. No, iron is not stable. The atom of the iron is not stable. Nucleus of the atom iron is stable. Clear? Because iron atom is not, because you see rusting happens, so many things happens with iron. It's not stable at all. But if you talk about the nucleus of the iron, it is very stable. It will never be radioactive. You will never see that iron is radioactive and it emits something, it emits alpha particle, beta particle. No, because it is one of the most stable nucleuses existed. Okay, so that was a graph. Now there are many confusions in this graph, which I understood after teaching it. So I have taught this topic 3-4 times, and I realized that people don't understand binding energy at all. And I can bet you, even till now, whatever I explained, you don't have any idea what I'm talking. Okay? So you don't understand binding energy that much. So now the next 5 minutes are very important. So that 5 minutes will actually going to decide how much you understand binding energy. Okay? Let's be very clear. So whenever you go from an unstable state to a stable state, so you have an unstable state and you go to stable state. Unstable state has less binding energy per nucleon. Less binding energy per nucleon. Okay, let me make that diagram. This is your unstable state. Now people think binding energy is the energy of the nucleus. No, it is not the energy of the nucleus. Don't get me wrong. Binding energy is the not energy of the nucleus. Binding energy is the energy required to make the nucleus. But after making the nucleus, what is the energy of the nucleus? That is a separate issue. Binding energy is like a well. Is like a well. So inside this well, all the nucleons are there. And if you want to break this nucleus, you want all these nucleons comes out. And then everything will fall apart and your nucleus will break. So the height of this nucleus, or the depth, sorry, not height, the depth of this nucleus or this well is the binding. Okay, so let's say this is unstable state and the depth is -4 megaelectron. -4. Okay. So yes, if you want to break this nucleus, what you have to do is you have to give this energy. So if I give 4 mega electron volt of energy to them, 4 mega electron volt of energy to them, that is the confusion. That is why I'm explaining this. That is the doubt people have. Okay, that is the doubt people have. Okay. So if I give 4 mega electron volt energy to them, so these nucleons will have now enough energy, so they will come out. Nucleus will break. Okay, so this is unstable. Unstable means comparatively unstable. Now, compared to this state, you see the depth is too much. Depth is now -8 mega electron. Okay? Depth is -8 mega electron. So binding energy increased. Magnitude of the binding energy increased. Negative sign is just telling you that it is a depth. It is a well. It is not a upper, it is niche. But the magnitude of the binding energy has increased. Initially it was 4, now it is 8. So now if I want to break the nucleus, how much energy I need? I need 8 mega electron volt of energy. 8 mega electron volt of energy. And this is stable because it needs more energy to break this. So whenever you go from unstable to stable state, the magnitude of the binding energy increases. Okay? So whenever you're going from unstable to stable, binding energy will always increase, because binding energy tells you. So usually people confuse it. With the energy of the nucleus. How? So whenever you go from stable to unstable to stable, energy decreases. Energy decrease. That is what we learn. Everything wants to be at a minimum energy. Okay, perfect. That idea is perfect. Everyone wants to get minimum energy. But binding energy is not a energy of nucleus. ये nucleus की energy नहीं है. This is not energy which nucleus has. It is an energy which you need to break the nucleus. It is not an actual energy that a nucleus has. So binding energy concept basically means with how much energy you can break this. So if you can break this with 4 mega electron volt, okay, or you can break it with 8. So yes, obviously 8-1 is more stable because you need more energy to break it. That is why whenever you go from unstable to stable state, magnitude of the binding energy increases. Okay? It does not mean the energy of the nucleus is increasing. No, binding energy of the nucleus is increasing because binding energy is the energy which you need to break the nucleus. And in a stable state, you need more energy. In unstable state, you need less energy. So whenever you go from unstable state to stable state, your binding energy per nucleon is increasing. It will always increase. Stable state has more binding energy. Unstable state has less binding energy. ठीक है, ये any doubt in this? Any doubt in this? Any doubt? Okay. And energy will release also. So if you go from unstable state to stable state, so let's say your nucleus decides to go from unstable to stable, it will emit the energy. It will give you some gamma decay, it will give you some beta decay, it will give you some alpha decay. So energy will be released whenever you go from unstable to stable. Obviously the energy will be released, but it does not mean that released energy is because of the binding energy. No. Binding energy is also increasing. Magnitude of the binding energy is going from 4 to 8. So your binding energy goes from 4 to 8, and you also emit the energy. ठीक है, because binding energy is not the energy of the nucleus. ठीक है, binding energy is an energy you need to break the nucleus. That is not an actual energy that you need. So important thing to remember is that energy is released whenever you go from unstable to stable, and your binding energy also increase when you go from unstable to stable. ठीक है, these two are the very important facts. And two things we can define from here is fission and fusion. ठीक है, energy needed for survival. So someone asked the question, energy needed for survival of nucleus, binding energy needed for the motion of nucleus. Yes, both are unreal. Yes, you are right. So yes, so now we talk about fission and fusion. That is going to be a good concept here. So two things can happen. Two things happen here. So one is that fission. Fission is what? Okay, heavy nucleus. You see, this is a heavy nucleus. So someone who is here is heavier. So this heavy nucleus breaks. So let's say this was 180. Okay. So let's say this is 112. This 112 breaks into 256. So you see, this was unstable because it has low binding energy per nucleon. These are stable because it has high binding energy per nucleon. That is why the nucleons which are here breaks and they comes in this region so that their binding energy can increase. Their binding energy can increase. That is why the heavier nucleus breaks itself and becomes two medium-sized nucleons, and these two medium-sized nucleons has more binding energy per. It means the heavier unstable nucleus comes to stable nucleus, because if your binding energy increases, if your binding energy increases, it basically means your stability increase. Now someone asked, so that was the confusion. Someone asked ki binding energy is also increasing and energy is also released. How? That is what I am telling कि देखिए, बाइंडिंग एनर्जी इज नॉट द एनर्जी ऑफ द न्यूक्लियस. मान लीजिए आपके पास पहले जो एनर्जी था दैट वाज 3. अब आपके पास जो एनर्जी है वो है लेट्स से 1. So 2 mega electron volt of energy will be released. So this was energy that your nucleus had. ये आपके पास वो एनर्जी है जो न्यूक्लियस के पास थी, जो है. बाइंडिंग एनर्जी वो एनर्जी होती है जो आपको चाहिए न्यूक्लियस को तोड़ने के लिए. ये एनर्जी न्यूक्लियस के पास है नहीं. बाइंडिंग एनर्जी जो है वो न्यूक्लियस के पास होती नहीं है. बाइंडिंग एनर्जी इज डिफाइंड इन अ वे कि ये एनर्जी वो एनर्जी है जो आपको चाहिए तोड़ने के लिए. तो पहले आपको कितना चाहिए था तोड़ने के लिए? 4. अब आपको कितना चाहिए तोड़ने के लिए? 8. तो बाइंडिंग एनर्जी बढ़ गया. लेकिन पहले आपके पास न्यूक्लियस के पास कितनी एनर्जी थी? 3. अब आपके न्यूक्लियस के पास कितनी एनर्जी है? 1. तो न्यूक्लियस की अपनी एनर्जी तो कम हुई ना. तो न्यूक्लियस की अपनी एनर्जी कम हुई तो वो फिर क्या करेगा? वो कुछ अमिट करेगा, और उस अमिशन की एनर्जी कितनी होगी? 2 मेगा. तो बाइंडिंग एनर्जी भी बढ़ गई, और एनर्जी अमिट भी हो गई. तो दोनों चीजें एक साथ हो सकती. दैट इज द कॉन्सेप्ट यू नीड टू अंडरस्टैंड. ठीक है, बहुत से लोगों को लगता है कि बाइंडिंग एनर्जी वो एनर्जी है जो न्यूक्लियस के पास होती है. ये कंफ्यूजन शुड नॉट हैव. ठीक है, अदरवाइज जो नेक्स्ट टॉपिक आएगा न्यूक्लियर रिएक्शंस, उसमें आपको प्रॉब्लम, उसमें आप समझ नहीं पाएंगे कि हो गया. वी विल डू वन क्वेश्चन लेटर, बट लेट्स कंप्लीट फिजन. फिजन इज बिगर न्यूक्लियस ब्रेक्स. तो बिगर न्यूक्लियस के पास कम बाइंडिंग एनर्जी थी, so it breaks and it gives you middle sized nucleuses तो इनके पास बाइंडिंग एनर्जी थोड़ी ज्यादा है, इसलिए स्टेबिलिटी बढ़ गई. एवरीवन वांट्स टू बी स्टेबल. सिमिलरली फ्यूजन में क्या होता है? इन फ्यूजन smaller nuclei combine together to give you a middle size nucleus. So you can see the smaller nucleus also has a low binding energy. So if they combine and they forms together, then you see binding energy per nucleon increases. So again the stability increases. So what you want to do is you basically wants to come to the middle. You want to come to the middle. आप यहाँ से भी middle में आना चाहते हो और यहाँ से भी. If you come from here, it means the fission is happening. Bigger one is breaking into smaller ones. And if you want to come from here, then you have to combine together to come together. 20 and 20 combine together to give you 40. 80 breaks into 40. Okay? So if you come to the middle, your binding energy is increased. So you are more stable. If you are here or if you are here, binding energy per nucleon is less. So you are less stable. So you want to come from here to here. That is the idea. Okay? That is a rough idea of fission and fusion. Okay? So any doubt in this? Otherwise, I will close this session after one question. So one question I will do related to this and then I will close it. Yeah. Any doubt, anyone? In binding energy concept. So someone asked that does binding energy per nucleon matter more or binding energy total of the nucleon? Binding energy per nucleon matters more. ठीक है, it will basically you have to see कि binding energy per nucleon increase हुआ या नहीं. ठीक है, semi magic numbers see क्या होता है कि then I don't know in which theory you are talking. Semi basically we are comparing the stability with the nucleus, neighboring nucleus, कि आसपास के न्यूक्लियस के कंपैरिजन में इसकी स्टेबिलिटी कितनी ज्यादा या कम है. ठीक है. So this is one question from IIT JAM. Interesting problem. So they are giving you a hypothetical binding energy graph. So they have given you a graph. You don't have to come up with your own graph. They have given you the graph of binding energy per nucleon as a function of A. So this is the following histogram. Histogram is a graph which is made like this. Represents the binding energy per nucleon in mega electron volt as a function of mass number. Okay. So what this says is a nucleus with mass number 180 fission. Fission means breaks into two nucleus of equal mass. So basically 180 breaks into 90 and 90. Okay. So where is your 180? So let's identify. So your 180 will be here. So what is the binding energy per nucleon? Binding energy per nucleon is 4. You see 4. Okay, it breaks into 90 and 90. So where is your 90? So this is your 90. So what is the binding energy per nucleon here? Binding energy per nucleon here is 6. So you see, you go from a less stable state to more stable because you see binding energy per nucleon has increased. So it means you have attained more stability. Fission has happened. So they says that in this process, what will happen? Energy will release or not? Yes, energy will release because whenever you go from unstable to stable, energy will always increase. Energy also increases and binding energy also increases. That is what I was telling you. How much energy will increase? Let's see. How much energy will be released? So what is my total binding energy first of all? What is my total initial binding energy? So my total initial binding energy is 180 into 4 because there are 180 number of nucleons and binding energy per nucleon is 4. So 180 into 4 will give me total energy which is 720. Okay. This was the total binding energy that I had. No, not I had, but that I needed to break the nucleus. Okay. Finally, I still have 90-90, which means I still have 180 nucleons. But now my binding energy per nucleon is 6. So now what is the energy that I have? 180 into 6, which is 1080. So what is the energy difference? Energy difference will be 360. Here comes the confusion because you go from a binding energy of 720 to a binding energy of 1080. Some people think, okay, since the energy is increased, it means energy is absorbed. Oh no, oh no, no. Binding energy is not energy that you have. That is the point. It does not mean that you absorb the energy. No, you release the energy because you are going from a unstable state to a stable state. Okay. So your binding energy is increased, which basically means that your well has now become even deeper. Okay, so well has become even deeper. So initially you were at minus 720, now you are at minus 1080. Okay? So let's say you were a person who had a debt of minus 720, मतलब उसको बैंक के 720 रुपए देने थे. Now अब उसको बैंक के minus 1080 देने. It means he has released the money. मार्केट में उसने खर्च कर दिए. How much he has खर्च, how much he has spent is 360. So he has released 360 rupees. That is why he go from minus 720 to minus 1080. ठीक है, तो बाइंडिंग एनर्जी का मैग्नीट्यूड बढ़ गया. बाइंडिंग एनर्जी का मैग्नीट्यूड बढ़ने का मतलब उधारी बढ़ गई. उधारी बढ़ने का मतलब है खर्चा हुआ है. कितना खर्चा हुआ है? 360 रुपए का. इट मींस 360 इज द अमाउंट ऑफ एनर्जी रिलीज्ड. सो दैट इज व्हाई ऑप्शन नंबर सी इज करेक्ट. ठीक है, सो व्हेनेवर यू गो फ्रॉम अनस्टेबल टू स्टेबल, binding energy increases, magnitude of the binding energy increases, and well becomes even deeper and energy is released. Okay, that is why in fission and fusion, in both the cases, energy release. So tomorrow what I'm going to do is give you a models of binding energy, semi-empirical formula, and we will do a lot of problems related to the binding energy tomorrow. Okay, so from here I will pick up, and now I will close the session here, and now I will meet you in the evening class at 7:30 with the second lecture of electronics revision. Okay, so that's all for this lecture.